Let me ask you a question. Reading one value from memory versus sending a network packet from California to the Netherlands and back. How many times faster is one than the other? 1.5 million times. If you treat one memory read as 1 second, that transoceanic round trip takes more than 2 weeks. 2 lines of code in the same program. One lives in a world of seconds, the other lives in a world of weeks. In system design, Lesson 1 isn't drawing architecture diagrams. It's burning this map of speeds into your brain first. Today, I'm going to install 3 things in your head: a latency numbers table, a powers of 2 table, and a back-of-the-envelope estimation playbook. Once they're in, where other people just guess, you can spend 5 minutes on paper and get an answer that's correct to the order of magnitude. And I'm not just going to take this on faith. This latency table has been floating around for over a decade. Today, I'm running real measurements on my own machine to see which numbers still hold up and which ones have gone stale. And along the way, I stepped into 2 absolutely beautiful traps. I'm saving those for later. First, the table. It has a big famous name, latency numbers every programmer should know, and it started as something Jeff Dean used in internal talks at Google. Read it top to bottom. 1L1 cache reference, 0.5 nanoseconds. 1L2 cache reference, 7 nanoseconds. 1 main memory reference, 100 nanoseconds. Read 4 KB randomly from SSD, 150,000 nanoseconds, which is 150 microseconds. A round trip within the same data center, 500 microseconds. A transoceanic round trip, 150 million nanoseconds, 150 milliseconds. From the top of the table to the bottom, that's 9 orders of magnitude, 300 million times. A span that big, the human brain has no intuition for. So let me rescale it for you. Blow that 0.5 nanosecond L1 cache reference up into 1 full second. Then 1 main memory reference is 3 minutes. 1 random read from SSD is 3.5 days. A round trip inside the data center, 11.5 days. And a transoceanic round trip, 9.5 years. This table is the map scale of the computing world. In the CPU's eyes, memory is the room next door, the SSD is the next city over, and a server on another continent is Alpha Centauri. Every line of code you write is walking somewhere on this map, and you'd better know which leg of the trip it's on. Now you might be thinking, only low-level engineers ever need these numbers, right? It's exactly the opposite. People who don't know this map crash in 2 different directions. Direction 1 is under design. You treat random reads, like sequential reads, querying the database 1 row at a time inside a loop. Runs fine locally on 10 rows. 1 day in production, the table has 10 million rows. 1 page fires 200 queries. Each round trip costs half a millisecond, and the page just locks up. The other direction is over design. An internal tool, 10,000 requests a day, which averages out to 0.1 per second. And you give it sharding, a message queue, and 3 replicas. That's not architecture. That's performance art. The cure for both diseases is back-of-the-envelope estimation. Rough numbers on the back of a scrap of paper worked out to the right order of magnitude. Google puts it in interviews not to mess with you, but because this is the actual day-to-day motion of the job. To estimate fast, you need the second table. The powers of 2 table. The core is 1 single trick. 2 to the 10th is roughly 10 to the 3rd. Add 10 to the exponent, multiply by another 1,000. 2 to the 20th is 1,000,000. 2 to the 30th is 1,000,000,000. And storage sizes follow right along. KB, MB, GB, TB. Each level is 1,000 times the last.
Pinning down a few conversion anchors. 1 nanosecond is 10 to the minus 9 seconds. 1,000 nanoseconds is 1 microsecond. 1,000,000 nanoseconds is 1 millisecond. For text, 1 English character is 1 byte, and 1 Chinese character in UTF-8 is 3 bytes. These anchors are in play for the rest of the episode.
Tools loaded. Now let's actually work a problem so you can see the moves. The problem. You're building a photo sharing app with 10 million daily active users. Servers, storage, bandwidth. How much of each? Sounds scary. We take it one item at a time. First, lay out the assumptions. 10 million daily actives. Each person posts 2 photos a day. Each photo is 500 KB after compression. For viewing versus posting, assume a 100-to-1 read-write ratio. Write the assumptions down on paper. If they're wrong, you go back and change the assumptions. That's the rule with envelope math. Item 1, write rate. 10 million people times 2 photos, 20 million photos a day. A day is 86,400 seconds. Just brutally round it to 100,000. Remember, we want the order of magnitude, not the decimal places. 20 million divided by 100,000 seconds is 200 writes per second. Traffic peaks, so multiply by 2. Peak is 500, give or take. Item 2, reads. Multiply the writes by 100. Over 20,000 reads per second, 40 to 50,000 at peak. Item 3, storage. 20 million photos times 500 KB is 10 trillion bytes a day, 10 terabytes. Keep it for 3 years. Multiply by a bit over 1,000 days. 11 petabytes. Item 4, egress bandwidth. 20-something thousand reads times 500 KB comes to about 90 gigabits per second, so you must put a CDN in front, or that bandwidth bill will burn the company to the ground.
Checking against the real run. Writes, 231 per second, peak 463. Reads, 23,000 per second. 10 terabytes of new storage a day. 10.9 petabytes over 3 years. Egress, 93 gigabits per second. Mental math versus the script. Error under 10%. Every order of magnitude correct. That's enough. For back-of-the-envelope estimation, the pass line is staying within a factor of 10.
Watch the sequence of moves. Lay out assumptions. Turn days into seconds. Scale up by the read-write ratio. Double for peak, and round hard at every step. Once it's drilled in, this problem takes 5 minutes. To estimate fast, you also pick a few golden ratios out of that latency table and memorize them. I'll underline 3. Number 1, main memory reference, 100 nanoseconds. SSD random read, 150 microseconds. 1,500 times apart. That's why caching shows up in every architecture ever drawn. Move data from disk into memory, and what you just bought is 3 orders of magnitude. Number 2, a disk seek on a spinning hard drive, 10 milliseconds. Flip it around, 1 second only buys you about 100 seeks, meaning one spinning disk tops out around 100 random IOs per second. If your database needs 10,000 random reads per second, on spinning disks alone, that's 100 drives. This one ratio single-handedly decides how many companies buy SSDs and add caches. Number 3, read 1 MB sequentially from SSD, 1 millisecond. Only 4 times slower than memory. On sequential reads, disk and memory are a few times apart. On random reads, 3 orders of magnitude. Hold on to those 3, and a lot of architecture decisions become math you can do on the spot. Okay, estimation is pencil work. But is this latency table itself even trustworthy? It's a table from over a decade ago. Time to bring out the real hardware and measure it. Experiment 1 measures memory. I wrote a little C program that chops an array into 64 byte cells, each exactly 1 cache line, chains them into a big randomized ring, and makes the CPU chase around it hop by hop. The key is that the address of the next hop is hidden inside the data of the previous hop. The CPU can't guess it, can't prefetch it, so what you measure is the raw memory access latency. And the result is this staircase. With the array at just 64 KB, everything fits in L1, 2.6 nanoseconds per hop. Grow it to 4 MB, and it drops into L2, 7 nanoseconds. Identical to the table's L2 row. Grow it again to 512 MB, no cache can cover it, pure main memory, 118 nanoseconds. The table says 100. A table from 2012, and its L2 and main memory rows are still accurate on my laptop today. but one row has aged. Read 1 MB sequentially from memory. The table says 250 microseconds. I measured 19. That's 13 times faster. Memory bandwidth has exploded over the past decade plus, so the absolute value moved long ago. But notice, the staircase is still the same staircase. L1 is still tens of times faster than main memory. Absolute values age. Ratios live long. Memorize ratios, not absolutes. Experiment 2 measures the SSD and the network. Read 4 KB randomly from SSD. Measured 199 microseconds. The table says 150. Same order of magnitude. Read 1 MB sequentially, 684 microseconds. The table says 1 millisecond. That checks out too. Then, the network. A loopback round trip on the same machine, 67 microseconds. And the prettiest one is this. A ping from California to a server in the Netherlands comes out at 160 milliseconds. And the table row, send packet California to Netherlands to California, says 150. Over a decade, and that number hasn't moved a hair. Why did the memory number change by a factor of 13 while the transoceanic number never moved? That question deserves its own layer. Because the transoceanic number isn't decided by engineering, it's decided by physics. Light in optical fiber covers about 200,000 kilometers per second. California to the Netherlands is nearly 9,000 kilometers along the route, 18,000 round trip. The speed of light alone eats 90 milliseconds. Add routers queuing and forwarding hop after hop, and 150 to 160 milliseconds is simply the floor. Moore's law has no authority over the speed of light. That's why CDNs haul content right up to your doorstep. It's not that servers are too slow. It's that the Earth is too big. The memory and SSD rows are decided by engineering, so they keep improving. But one structural thing outlives all the numbers. Sequential beats random. When you read sequentially, the hardware is betting that you'll keep reading. The CPU's prefetcher pulls the upcoming cache lines in ahead of time. The SSD controller has the next page pre-turned, and by the time you arrive, the data is already there. With random reads, the bet is off. Every access honestly pays for a full round trip. Same 1 MB of memory. Sequential, 19 microseconds. Random hops at 118 nanoseconds per cache line, nearly 2 milliseconds, 100 times apart. Why databases love B-trees, why logs are append only, why Kafka is fast. The root of all of it is this one line.
Nailing down one more classic comparison. Sending 1 KB over a 1 gigabit per second network, 10 microseconds. Reading 4 KB randomly from SSD, 150 microseconds. Which means the memory of another machine in the same data center is closer than the disk under your own machine. That one conclusion directly spawned the memcache generation of architecture. Better to put your cache and memory across the network than on the disk at your own feet. And one set of frequency anchors. Inside a data center, you get 2,000 round trips a second. Across the ocean, 6 or 7. So 1 cross data center call inside a request should make you nervous. 3 is an incident.
We still have to cover the failure path. These numbers are not constants. This table lists ideal single operations. In a real system, what you worry about is the tail. A disk that averages half a millisecond can be tens of milliseconds at P99. Queues build up, utilization crosses 80%, and latency takes off exponentially. Envelope estimation gives you the sunny day map. Capacity planning still has to leave headroom for storms. More on that later. Our regular segment. How is AI going to shake this up? This episode, the answer splits in 2. One half, this table has grown a brand new column in the AI era. The other half. The craft itself is exactly the thing AI can't replace. The new column first. When you call a large language model today, what is the latency you feel actually made of? Number 1, time to first token. The model has to chew through your whole prompt before it spits out the first word. That one is compute bound. Number 2, generation speed. How many tokens per second? That one is bandwidth bound. Number 3, the KV cache. The GPU memory, the model needs to remember your context. That one is capacity bound. 3 new latency numbers, exactly the same animal as the table we just walked through. And the envelope playbook transfers over untouched. I actually ran it on a 70 billion parameter open source model. The weights: 70 billion parameters times 2 bytes each in FP16, 140 GB. That doesn't fit on one 80 GB card, so you start at 2 GPUs. The KV cache. Work it out from the model's structure, 328 KB per token. An 8K token context takes 2.7 GB per stream. After the weights, the 2 cards have 20 GB left, so they can only serve 7 conversations at once. Generation speed. Every token it produces has to drag all 140 GB of weights through GPU memory once. Divide by the memory bandwidth, and one stream caps out at 48 tokens per second. Layer on the GPU rental cost, and the order of magnitude lands around $6 per million tokens. Time to first token also comes straight off the envelope. Rule of thumb. Processing one token takes about twice the parameter count in floating point operations. An 8,000 token prompt times 70 billion parameters times 2, over a quadrillion operations. 2 cards flat out supply about 2 quadrillion operations per second. Cut that in half for real-world efficiency. First token, about 1 second. That 1 second you spend waiting for the model to think? It's a bill you can compute on the back of an envelope.
The interesting part is that API prices on the open market run quite a bit below this envelope number. That gap is not magic. Quantization squeezes 2 bytes down below 1. Bigger batches spread out the weight hauling, speculative decoding, purpose-built inference stacks. The envelope tells you how big the gap is. And that gap is their engineering.
So, can AI do the estimating for you? Helping, yes. Replacing, no. Looking up formulas or recalling memory bandwidth specs, it does that faster than you can flip open the docs. But a large model doing its own arithmetic will put digits in the wrong places. Every number it hands you, you verify with your own order of magnitude intuition. Without that intuition, it can be off by a factor of 1,000, and you'll nod along and say looks great. The historical anchor for this is the calculator. Calculators going mainstream didn't kill mental math. They killed the people with no feel for magnitudes, the ones who couldn't tell when a digit was off. The one who gets hit hardest is the engineer who takes model output at face value and never checks the numbers. The stronger the tool gets, the more that number-checking instinct is worth. This episode installs exactly that instinct. Before we wrap up, the 2 traps I genuinely stepped in during these tests. They're worth more than the conclusions. Trap 1. My first pass at the SSD test, 4 KB random reads, came out at 1.1 microseconds. More than 100 times faster than the table. I almost believed it. Then I took a breath. That can't be right. That 2 GB test file had just been written, and the whole thing was still lying in the operating system's page cache. I wasn't measuring the SSD at all. I was measuring memory. On macOS, you have to flag the file descriptor to bypass the cache on both the write and the read, and the number instantly got honest. 199 microseconds. The lesson in 1 sentence. When a number is too good to be true, doubt your measurement first, and the world second. The second trap is sneakier. At first, I was using the TCP handshake time to estimate network round trips, and a server in Finland came back at just 18.6 milliseconds. But you just took the speed of light class. California to Helsinki, the light speed floor alone is nearly 90 milliseconds. 18 milliseconds is physically impossible. I dug in, and a middle box on the path was answering the handshake on the remote server's behalf. The handshake timing was worthless. Switching to ping finally measured the real number, 189.6 milliseconds. See, order of magnitude intuition isn't just for estimates. It's also your lie detector. The speed of light is the best sanity check there is. Last, the boundaries. Back of the envelope estimation is an order of magnitude tool. Don't hand it in as the final draft of your capacity plan. It ignores P99 tail latency, it ignores hotspot skew, it ignores bursts. Its job is to spend 5 minutes in a meeting room and settle whether one machine is plenty or this thing has to go distributed. Rough, but pointing the right way. Get the direction right, and only then does precision math mean anything. One line to wrap it up. The latency table? Powers of 2, back of the envelope estimation. Install all 3, and you own a coordinate system. The numbers drift every year. You watched one row age by a factor of 13. So don't memorize absolute values. Remember the staircase, remember the ratios, remember the moves. And I'm leaving you something you can actually run. Both benchmark scripts are in the description. A few dozen lines each, 0 dependencies. Take them, run them on your own machine, and measure the latency table that belongs to your hardware. You'll remember it 10 times better than watching me do it. Once you have the coordinate system, the next question walks in on its own. When the math says one machine can't carry the load, do you buy a bigger machine or do you buy more machines? That's the main event of the next episode. See you next time.